In this video, we work a bunch of additional examples of antidifferentiation by substitution. And this is from section 5.4 on exponential functions. Some of these problems aren't from the 5.4 exercises, but I've modified some of the 5.4 exercises to create this list. It's just a bunch of antiderivatives. Pretty much they're all going to refer back to one of our basic rules. The antiderivative of e to the u with respect to u is just e to the u plus c. Now, the basic rule is usually stated the antiderivative of e to the x with respect to x is e to the x plus c. But in all of these, we're going to do a u substitution first, and we're going to end up with pretty much all of them, a constant times e to the u for our antiderivative. There's actually, I think, maybe one or two examples where we don't do that. Okay, so we look at this problem and we say to ourselves, do we have a rule for that? And we say, no, I don't actually have a rule for that because I've got a product here and there's no product rule for antiderivatives. It turns out that there is a sort of product rule in reverse thing that we do called integration by parts that we'll learn in calculus 2. But for now, there's not just a formula that you can use for the antiderivative of f of x times g of x. So you say, okay, if I've got a product and that's not one of my basic rules, I need to use u-substitution. That's our most advanced tool. So we look for a function nested inside of another function. And I see this exponential and I see that there's an x cubed inside that exponential. So I'm not sure this is going to work, but I will choose u equals that inside function x cubed. And basically this is how we'll do all of these problems. We'll choose our u. And that's provided that we don't have a basic rule for the original integrand. And let me write the technique. We're going to say, we're going to antidifferentiate using u-substitution. So we let u equal x cubed, and then we compute du. Now, when we compute du, that will tell us whether or not this can be evaluated, this integral can be evaluated using u-substitution. Now, du is just the derivative of u times dx. The derivative of x cubed can be found using the power rule. You bring the 3 down, then you multiply by x to the 1 less power. Don't forget your dx. And then you look for this up there. Now, we don't need this exact expression, but we want to have at least a multiple of this expression. We're looking for the x squared dx in particular. Do we have an x squared dx? And we do. We have an x squared dx right there. So that means I don't need this 3. So I'll multiply both sides of the equation by 1/3 to solve for that x squared dx. And it turns out that x squared dx that we actually have in the integrand, that times that, can be replaced by 1/3 of du. So now we write the integral entirely in terms of u. We've got e to the u power. And this x squared dx can be replaced by the 1/3 du. I'll put the 1/3 on the far left and the du on the far right. So what did we do? We chose du. We computed, or chose u, excuse me, the inside function. We computed du, and then we solved for x squared dx, because that was the extra factor multiplying that exponential function. And then we say, do I have a basic rule for that? And we certainly do. The antiderivative of e to the x with respect to x is just e to the x plus c. So the antiderivative of 1/3 e to the u is going to be 1/3 e to the u plus c. So that is our antiderivative, but we're not finished until we back substitute. We need a function here that if we take its derivative, we get the original integrand back. So we need to, after we antidifferentiate, substitute u equals x cubed into our final answer, and that will be our final answer. So antidifferentiate, and we call this back substituting. In other words, we're just replacing this u with an x cubed. So you have 1/3 e to the x cubed plus c is our antiderivative. And I like to put my antiderivatives in a box. Now, if I differentiate this, I'll have 1/3 times the derivative of e to some power. That'll be e to that power times the derivative of the inside. Now, the derivative of that x cubed is 3x squared. That 3 times the 1/3 will give me just a 1 coefficient. And so we'll have an x squared times e to the x cubed. And that's our original integrand, plus the derivative of a constant, which is just 0. So that is our antiderivative. Let's do another one. Okay, with this one, you actually have options. If you wanted, you could write this e to the 3x plus 4 5 times. Then you could distribute, you'd have a binomial times a binomial, and then you'd have a trinomial times a binomial, and then you'd have what I think it would probably have 4 terms multiplied together. And you could keep doing that. I mean, it would take a long time, but you could just do all the algebra, and then eventually you'd multiply every term in the expression by e to the 3x, remembering that we've got some exponent properties. If I have a power raised to a power, we multiply those exponents. And if we have a power times a different power, you just add the exponents. We have the same base. So we might use this rule if necessary. But we might also use u-substitution. There might be an easier way. So again, I'm looking for an inside function. If I don't have a basic rule, and we don't have a basic rule unless we do a bunch of algebra first, I'm looking for a function nested inside another function. Usually that's indicated by some parentheses, some kind of, or some other kind of grouping symbol. So maybe the expression is under a radical, or it's in parentheses, or it's inside an exponential function, or inside a trig function, something like that. As soon as I see that I've got those parentheses there, I've got that function raised to the 5th power, I'm thinking, maybe this will work. Maybe that inside function, e to the 3x plus 4 should be my u. Now, I've had students before say, well, why don't I just let u equal e to the 3x? Why won't that work? Well, it will work, but what you'll end up with is a u plus 4 to the 5th, and then you'd have to do another substitution. You'd have to do a w substitution for that. So you'd have to let w equal u plus 4. And that would take a really long time. So we can avoid that by including that extra constant in our original choice for u. So we're going to choose u to be an inside function. And that was indicated by those parentheses that suggested that maybe that function inside will be our u. And we compute du. Now the derivative of e to some power is e to that power times the derivative of the inside. And the derivative of the inside in this case is the derivative of 3x, which is just a 3. And we multiply by dx. And then we look at this, and we're never really sure u-substitution is going to work until we compute du, and then we look at this. We say, okay, do I have a 3 times e to the 3x dx? Or some multiple of that? We can always adjust the constant. And we say, yes, we do. We actually have an e to the 3x dx right there. So I don't need this 3. So I'll multiply both sides of the equation by 1/3. Solving for that e to the 3x dx. So we chose u, we computed du, then we solved for what we had in the integrand, that e to the 3x dx. And then we want to write the integral entirely in terms of u. So we say, okay, I'm literally replacing things. So this is literally a u. That's what u is. So I'm going to have a u to the 5th there. And this e to the 3x dx is 1/3 of du. So we put a 1/3 on the far left and a du on the right. And we say, do I have a basic rule for that? And we do. It's just a power rule. So we add 1 to the exponent. It's going to give us a u to the 6th. And then divide by the new exponent. Dividing by 6 is the same as multiplying by 1/6. Don't forget your plus c. So we end up with a 1/18 times u to the 6th. But we want a final answer in terms of x, not u. So we replace u with whatever it was originally. In this case, u was that e to the 3x plus 4. And then don't forget your plus c. Now, if you differentiate this using the power rule, you will get the right answer. It's the power rule with the chain rule, right? Because we've got a function inside another function. U-substitution is basically undoing that chain rule. So I see, okay, when I take the derivative of this, I have to use the chain rule. Well, what's the derivative of the outside? It's going to be 1/18 times the derivative of this function to the 6th, which is 1/18 times 6 times the function to the 5th. That 6 times the 1/18 is going to give us a 1/3 out front. So we're going to have 1/3 times this function raised to the 5th power times the derivative of the inside by the chain rule. What's the derivative of the inside? Well, it's going to be e to the 3x times the derivative of 3x, which is just the 3. So we have the 1/3 times the 3. That'll be gone, and then we'll have an e to the 3x as an extra factor out front, and we'll have an e to the 3x plus 4 closed quantity raised to the 5th. And that is actually our original integrand. So we see that the u-substitution works. So we chose an inside function, we compute du, we solve for whatever we have, that extra factor here. It's going to be tends to be some function of x times dx. And then the goal is to write the integral in terms of u. And our hope is that after we write that integral entirely in terms of u, that we'll have a basic rule. Now, sometimes we make a u substitution or we make a particular choice and we still don't have a rule for it, so we might have to substitute again. But that's what we do. We write the integral in terms of u. If we do have a basic rule, because we chose u wisely, we antidifferentiate. And then don't forget to back substitute to get a final answer in terms of x. In this case, we had u equals e to the 3x plus 4. So we just replace this u with e to the 3x plus 4, and then we're done. All right. Now this one, I've got e to the 2x plus 2 e to the x plus 1, all divided by 3 times e to the 5x. Now, do I have a rule for that? No, I don't have a quotient rule for antiderivatives. But I see I've got multiple terms up here and just one term in that denominator. That one term in the denominator leads me to think maybe I should, what I call, separate the numerator. I can write this as a sum of 3 integrals or 3 antiderivatives. It'll be this divided by the denominator plus this divided by the denominator plus the 1 divided by the denominator. So I have e to the 2x divided by 3 e to the 5x plus 2 e to the x divided by 3 e to the 5x plus 1 over 3 e to the 5x. And then we've got to use some exponent properties to simplify that. If you have x to some power divided by x to a different power, you just subtract the exponents. We do the same thing here, even though the variable is in the exponent rather than being in the base. We'll have e to the 2x divided by e to the 5x is e to the 2x minus 5x. 2x minus 5x is negative 3x. Now we also want to factor out any constants first. There's an implied 1 there. So there's actually a fraction of 1/3 multiplying that e to the negative 3x. So you have 1/3 times e to this 2x minus 5x, which is e to the negative 3x, because you're subtracting the exponents. We do the same thing here. We notice the 2/3, so we write that down. And then we have e to the x divided by e to the 5x is e to the x minus 5x. X minus 5x is negative 4x. And then here we've got a 1/3. And that e to the 5x is in the denominator. That's the same as this. If I've got a 1 over x to the n, I don't have a basic rule for that, but I can bring that x to the n up to the numerator if I make the exponent negative. So this is a 1/3 times e to the negative 5x. Now here is a basic rule that you should learn. Whenever we take the derivative of e to the kx, we get e to the kx, right? Because of the chain rule. The derivative of e to some power is e to that power times the derivative of the inside. If the inside function is just a constant times x, the derivative of the inside is just the constant. So we get k times e to the kx in that case. That's when we take the derivative. Now, if we take the antiderivative, basically we're doing this backwards. The antiderivative of e to the x would be e to the x plus c. But if I have to use the chain rule to take the derivative, I would actually end up multiplying by that derivative of the inside. So I'd multiply by that k. When we do this backwards, we end up dividing by that k. So we're going to have 1 over k times e to the k plus c. Because if I differentiate this, I'll have 1 over k times e to the kx times the derivative of the inside. When I multiply by that k, that extra k times the 1 over k gives us a 1 for our coefficient. You could also do a u substitution, but it seems kind of like overkill, right? If we let u equal kx, du is k dx. So if I'm solving for dx, I end up with 1 over k du equals dx. So this ends up being 1 over k times the integral of e to the u du. Because this is my e to the u. The dx is the 1 over k du. So then we end up with 1 over k e to the u plus c, which is 1 over k e to the kx plus c. I actually don't ever do this u substitution. I just think of doing this in reverse. If I take the derivative of e to the 3x, I'd multiply by an extra 3. If I take the antiderivative of e to the 3x, I divide by an extra 3. because when I take the derivative, I would multiply them, and that 3 and the 1/3 will cancel, and we'll just get a 1 as our coefficient, which is what we've got right there. So with that in mind, I notice I've got a kx there, a kx there, and a kx there. So k is -3, k is equal to -4, k is equal to -5, and we've got these coefficients out front. So when we take the antiderivative of this 1/3 times e to the kx, we're going to have 1/3 times e to the kx, and then we'll divide by k. So we're going to divide by a negative or 3, which is the same as multiplying by -1/3. And then here we've got a 2/3, and the antiderivative of e to the kx is e to the kx. And then we'll divide by k. So we can divide by -4 or multiply by -1/4, same thing. Then we'll add 1/3 times e to the kx. Antiderivative of e to the kx is e to the kx. And we divide by -5, which is the same as the multiplying by -1/5. Don't forget your plus c. That's our final answer. It's just not simplified. We'll multiply those fractions straight across. So we get -1/9 e to the -3x minus, well, 2 goes into 4 twice. We're going to end up with -1/6 e to the -4x minus 1/15 e to the -5x plus c. And if we differentiate this, we'll have -1/3 or -1/9 times -3, that's the derivative of the inside, times the e to the 3x. The -3 times the -1/9 is going to give us a positive 1/3, which is our coefficient right there. And when I take the derivative of this, I have a -1/6 times e to the -4x times the derivative of the inside, which is a -4. So I have -4 times -1/6, which is positive 4 divided by 6, which simplifies to 2/3, which is our coefficient right there. And then with this one, if I take the derivative of e to the -5x, I've got e to the -5x times the derivative of the inside. So I have a -5 times a -1/15. That's going to give me a positive 5/15 or 1/3, which is our coefficient right there. And of course, the derivative of c is 0. So that is that. It is as, we can think of it as a simple u-sub, just u equals -3x, u equals -4x, and u equals -5x. But I find that if you memorize this rule, it's much faster. If you've got a kx inside, when you take the antiderivative, make sure to divide by k or multiply by the reciprocal of k, and that will always get you the right answer, and you can avoid doing recent u-substitutions. Okay, so now we're here. So do I have a basic rule for that? I've got a product here. No, I do not have a basic rule for that. So now I'm looking for a function inside another function. Now, whenever you see trig functions, remember you always have to take the cosine, sine, tangent, whatever it is, of something. Like you can't just have like tan by itself. You have to put something inside it. So when I see this cosecant, the first thing I notice is I've got that e to the 2x there. That is inside my cosecant function. So I'm going to use a u-substitution where u equals that e to the 2x. Oops. So we'll have u equals e to the 2x, and then we'll compute du. Du is the derivative of e to the 2x, which is e to the 2x, times the derivative of the inside, which is an extra 2, times dx. So in order to do this, in order to evaluate this, I need to write everything here in terms of x. Now, I look at my du in order to make sure that I can actually do the u-substitution, excuse me. I look at my du and I say, do I have a multiple of this 2 times e to the 2x dx? I'm not worried about the 2. I can always adjust the constant. But I said, do I have this e to the 2x dx up there somewhere? And I do. I've got an e to the 2x dx right there. So I don't need the 2. So I'll multiply both sides by 1/2. And that means our e to the 2x dx can be replaced by a 1/2 du. And you say, okay. Now let's write everything in terms of u. This piece is cosecant of u. Then the e to the 2x dx is 1/2 of du. You can say, do I have a rule for that? And the answer is yes, we do have a rule for it. It's not one of those that it might not be one of those that we have committed to memory. So you can memorize that if you want to. I'm going to show you how we do this using u-substitution again. Whenever we have cosecant, the antiderivative of cosecant or secant, it turns out that the way that we can solve this or evaluate this integral is by multiplying by a well-chosen one. And it turns out that the well-chosen one we multiply by is cosecant of your variable plus cotangent of your variable divided by itself. You say, why would we do that? Well, you'll see. So we're just multiplying by a well-chosen one. Now, if I think of that cosecant of u as itself over 1, when I distribute in the numerator, I have a cosecant squared u plus cosecant of u cotangent of u, all divided by cosecant of u plus cotangent of u. And we're anti-differentiating this with respect to u. So you say, do I have a rule for that? Absolutely not. But I might have a rule if I use another u-substitution. We already use u-substitution to get here. I still don't have a rule for this, but if I let some new variable equal my denominator, I might actually be able to evaluate this integral using a basic rule. So we're not sure it's going to work, but let's just try w equals cosecant of u plus cotangent of u. Okay, well, what is dw? What's the derivative of this times du, right? So, well, what's the derivative of cosecant of u? Well, it's negative cosecant of u times cotangent of u. And then what's the derivative of cotangent of u? Well, it's negative cosecant squared u. All of that is multiplied by du. And we say, do I have a constant times this in here somewhere? And we do. It's written in a slightly different order, excuse me. But we do have something that looks just like this up here. I've got the cosecant squared of u plus cosecant of u cotangent of u. The only thing is it's multiplied by this -1. So I'm going to multiply both sides by -1 in order to make that expression on the right equal to my numerator. And if you want to, you can distribute. So if I multiply that -1 through here and then change the order so that it looks more like our numerator, we've got cosecant squared u plus cosecant of u cotangent of u du is equal to -1 times dw. And you say, okay, now I want to write the integral entirely in terms of w. So we've got, still got that 1/2 right there. And then this denominator is w. And this cosecant squared u plus cosecant of u cotangent of u times du, that expression is equal to -1 times dw. So I'll put the negative outside and the dw on the far right. And then there's an implied 1 in that numerator. And then we say, do we have a basic rule for that? We do. The antiderivative of 1 over x is natural log of the absolute value of x plus c. So the antiderivative of -1/2 times 1 over w is -1/2 times natural log of the absolute value of w plus c. So now we're not done until we get a function of x. We say, okay, well, what was w? Well, w is this cosecant of u plus cotangent of u. So we're going to substitute that. Say, do we have a function of x yet? No. Well, why? Because we've got this u in it. And so, well, what was u? Well, u was e to the 2x. So now we're going to substitute that. That's an e to the 2x there and an e to the 2x there. So that is our antiderivative for final answer. We have a -1/2 natural log of the absolute value of the cosecant of e to the 2x plus cotangent of e to the 2x close absolute value plus c. If you take the derivative of this, you have to use the chain rule twice. You'll have -1/2 times 1 over this inside function times the derivative of the inside. When you take the derivative of the inside, you're going to get a cosecant cotangent of that e to the 2x times the derivative of e to the 2x. And then you're going to have a -1 times that. And here you're going to have a negative cosecant squared times the e to the 2x times the derivative of the inside. It's going to be a 2 e to the 2x. So you're going to have a 2 e to the 2x from here and a 2 e to the 2x from here. There are negatives in both of those derivatives. The negative times this negative makes a positive. The extra 2 factors from the chain rule from these guys cancels with that 2. And what you end up with is this expression. Well, actually, I think we end up with this. but instead of u's, we've got each of the two x's in it. Oh wait, no. I'm sorry. We end up with this expression, but we've got the e to the two x's in it, and then we can say, okay, let's factor out a cosecant of u, and then we'll have a cosecant of u plus cotangent of u in the numerator and denominator. Those will cancel, and we'll just get this, which will be equal to this, and that is our original integrand. So if you want, you can check your work by differentiating this, and it turns out if you do the work, use the chain rule twice and simplify, you're going to get that original that original integrand back, because the derivative of the antiderivative should be the original integrand. All right, I think that that's it for our additional problems for antidifferentiation by substitution. If you are a TCC student, you can do the integration B in the spring semester. Usually we do it in April. We do a lot of u-sub problems, a lot of integration by parts problems, and a lot of the techniques that you learn in calculus too. So these are really important for that if you're preparing to be in the integration B. But again, they all have a tendency, or at least these ones involving the exponentials, they have a tendency to look like this, or have an inside function that depends on e to the x. Like with this one, we had a power function where the inside function depended on e to the x. This one, we had to use algebra to separate the numerators and then simplify. And then we had an e to the kx rule that we decided to cover. And then with this one, we said the e to the 2x was on the inside of the trig function. And then we used that multiplying by a well-chosen one technique to make it possible to antidifferentiate this using another substitution. We couldn't use u because we already used that variable, so we called it w. So it's technically a double u substitution. Get it? Anyway. And then you antidifferentiate and back substitute, and that gets you your final answer. All right, so we are done with that. In the next video, we'll do some integration by substitution problems where we actually look at some areas under curves. And then we'll be done with 5.4, and we can move on to some other problems involving exponential functions with different bases. Rather than base e, we might look at a to the x. And we also have some really interesting application problems. We'll just cover an application problem or two in section 5.5. And then we will talk about, I think, inverse trig functions and hyperbolic functions, and we'll be done. So that's it for the antidifferentiation part. We'll do integration by substitution in the next video.